A gleaming blade can survive a millennium without a single spot of rust. This video reveals the astonishing metallurgical secrets that allow ancient artifacts to defy corrosion, a mystery locked in their atomic structure. By the end, you will understand how lost knowledge from the forge could revolutionize how we build everything today. How did a massive iron pillar stand for over 1,600 years without rusting away? What forgotten technique created a sword that could slice through silk? This journey uncovers how ancient craftsmen achieved feats modern science is still working to fully explain. It is not just about old metal. It is about a sophisticated understanding of the material world that has somehow slipped through time. So what does the enduring strength of the past say about our own fragile creations? That silent question is etched into the very surface of the iron pillar of Delhi. Rising over 22 feet high, this ancient column of wrought iron has endured the monsoon rains and humidity of India for more than 1,600 years. Yet its surface remains smooth, bearing a dark, protective layer rather than the flaky, destructive rust we expect. It stands as a direct, physical challenge to our modern assumptions. This is the core mystery we are unpacking: corrosion resistance. In simple terms, it is a material's ability to fight off the relentless chemical attack from its surroundings, to remain itself despite everything the world throws at it. For a piece of iron to display this property for centuries is not just lucky. It is a message from the past, a form of communication. As noted by materials expert Dr., these artifacts are not just surviving. They are communicating a sophisticated understanding of their environment. To hear that message, we first need to understand the language of decay itself. The enemy is a process called oxidation, and for iron it manifests as rust. Think of it as a silent, inevitable battle happening at an atomic level. When iron is exposed to both oxygen and moisture, a tiny electrochemical reaction begins. The metal essentially gives up electrons, transforming into a different, weaker compound, iron oxide. This new compound is brittle, crumbly, and takes up more space than the original metal. That expansion is why rust seems to bubble and flake off, exposing fresh metal underneath to continue the destructive cycle. It is a one-way street toward total disintegration. Given this, the fate of any iron object left outside should be a foregone conclusion. It should succumb. So when we encounter an object like the Delhi pillar, which has been exposed to those very elements for a millennium and a half, its pristine condition does not just defy expectation. It defies a fundamental law of chemistry as we commonly experience it. This foundational puzzle is what makes the ancient solutions we are about to explore not just clever, but truly revolutionary. They found a way to stop the one-way street. The first line of defense against time was not a coating, but a transformation of the metal itself. Ancient metalworkers discovered that by blending different elements together in the forge, they could birth an entirely new material, one inherently tougher and more resilient than its parents. This practice, intentional alloying, represents a monumental leap in human ingenuity. It was not accidental. A Bronze Age smith, for example, would deliberately combine copper with a specific rare tin ore. He may not have understood atomic theory, but through trial, observation, and passed-down wisdom, he knew the resulting metal bronze was harder, held a sharper edge, and crucially resisted the green, corrosive verdigris that slowly consumed pure copper objects. He was, in effect, programming the metal's behavior from within. This knowledge became a form of power, often closely guarded. Centuries later, medieval texts like those of the monk carefully recorded recipes for metal mixtures, treating the formulas with the secrecy of alchemy. The goal was always to engineer a superior substance. Adding tin to copper did more than just harden it. At a microscopic level, it created distinct phases within the metal matrix. Some of these phases were chemically less reactive, forming a more stable partnership with the environment. A high-tin bronze, for instance, naturally develops a thin, adherent patina, a protective skin that actually shields the softer metal beneath from further attack. It is a perfect example of ancient material science, using chemistry to force decay to work in the object's favor. But alloying was not limited to bronze. In other regions, craftsmen experimented by adding arsenic to copper, creating an even harder material in the centuries before tin became widely available. The principle was the same: manipulate the fundamental recipe to achieve a desired outcome, in this case, a metal that would last. This deliberate manipulation of composition was humanity's first and most direct declaration of war on decay. It was a loud, powerful method, reshaping the very essence of the material. Yet, the most elegant and enduring solutions are often the quietest. This pursuit of permanence would soon lead to the discovery of an even more subtle and powerful phenomenon, one where the metal learns to protect itself with a shield only a few atoms thick. That protective patina on an ancient bronze statue is not a sign of age, but of genius. This serene green hue, often admired for its beauty, is in fact a microscopic fortress. It represents the second, and perhaps most elegant line of defense, the magic of passive films. Unlike flaky rust, which accelerates destruction, a passive film is a thin, tightly bonded layer of oxide that forms on a metal's surface and then stops. It acts as a barrier, dramatically slowing any further reaction with the environment. Think of it as the metal growing its own perfect, protective skin. You can see this principle at work on Roman copper coins, known as eyes. Over centuries, a stable layer of copper carbonate, that distinctive green-blue patina, forms and seals the metal beneath from the air. It is a self-limiting reaction, a ceasefire negotiated at the atomic level. As materials scientist Professor Liam explains, a perfect passive film is like a self-healing skin for metal. If it gets scratched, the exposed metal quickly reacts with the environment to form a new protective layer in that exact spot, healing the wound. The chemistry behind this is fascinatingly simple in concept. For some metals, like copper or chromium, the initial oxide that forms is not loose and porous. It is dense, adherent, and chemically stable. Chromium oxide, for instance, is the invisible shield that gives stainless steel its name. When chromium is added to iron, it reacts with oxygen first, forming an ultra-thin, continuous layer over the entire surface. This layer is so effective, it prevents oxygen from ever reaching the iron atoms underneath, stopping rust before it can begin. Ancient metalworkers may not have known the molecular formula for copper carbonate, but through meticulous observation, they absolutely learned to recognize and even encourage this process. They saw that a properly made bronze object, over time, developed a handsome, stable green coating that preserved its form, while a poorly made one would crumble into powdery, destructive corrosion. This distinction was not lost on them. It raised a profound and practical question, one that would drive innovation forward. If a metal could grow its own armor naturally, could a craftsperson force that process to happen immediately in the forge, bestowing permanent protection from the very first day? The pursuit of that answer led to the most hands-on and visually dramatic secrets of all, the art of intentional surface treatment. The forge was only the beginning of the craft. After shaping and alloying the metal, ancient artisans turned their attention to its outermost frontier, the surface that would meet the world. Here, they developed a third protective layer, not grown from within like a passive film, but deliberately applied, a final shield painted, rubbed, or fused onto the metal itself. Picture a Mesopotamian craftsperson carefully rubbing a precious oil onto a ceremonial dagger's blade. In that simple, ritualistic act, they were unknowingly applying a primitive hydrophobic coating, repelling moisture long before the word was invented. This was the realm of ancient surface treatments, a diverse and ingenious toolkit for isolation. The methods ranged from the beautifully organic to the intensely technical. Organic barriers were some of the earliest and most accessible. Beeswax, tree resins, and plant oils were smeared onto metal objects to create a physical barrier against air and moisture. In East Asia, this practice reached an artistic and scientific peak with the famed Japanese lacquer derived from tree sap. When applied to metal fittings, perhaps on a samurai's sword guard, this lacquer cured into an incredibly hard, glossy, and nearly impervious shell. It was resistant to water, acids, and even mild heat, a testament to finding powerful solutions in the natural world. But some craftsmen sought not just to coat the metal, but to transform its very skin. This led to techniques like cementation, a process of profound subtlety. An iron object would be packed inside a clay container surrounded by charcoal or other carbon-rich organic material, then sealed and heated for days. During this long, slow bake, carbon atoms from the charcoal would gradually diffuse into the surface of the iron. The result was not a coating you could peel off, but a graded transition. The outermost layer became a form of steel, much harder and more corrosion-resistant than the soft iron core. It was case-hardening, giving a tool or weapon a resilient shell while keeping a tough, flexible heart. Another widespread method was tin plating, famously used on Roman artifacts like mirrors, jewelry, and tableware. Artisans would dip a cleaned copper or bronze object into a bath of molten tin, or sometimes rub solid tin onto it while heating. The tin bonded to the surface, creating a bright, silvery, and highly protective layer. Tin resists corrosion far better than copper, and its oxide is stable and toxic, making it perfect for items that came into contact with food and drink. Each of these techniques, from the simple application of wax to the complex chemistry of cementation, reveals a shared, practical understanding. The goal was always isolation, to place a durable, unreactive barrier between the vulnerable metal and the corrosive agents in its environment. It was a direct, hands-on intervention, a final step of craftsmanship that shouted a clear intention: this object is meant to endure. Yet, for all their skill in manipulating the metal and shielding its surface, the wisest artisans understood something even more fundamental. True longevity required listening to the world the object would inhabit, and sometimes making a deliberate choice to hide it away entirely. The most profound protection for an artifact often came not from the smith's hand, but from the earth itself. While a craftsman could forge a resilient alloy and coat it in a protective layer, the final guardian of an object's longevity was frequently the specific environment in which it was placed. This is the subtle art of environmental mastery, where the very conditions of burial or storage become a silent, enduring preservative. Think of the perfectly dry, still air inside a sealed Egyptian tomb. Here a polished copper mirror could lie for, its surface untarnished, because the environment actively the two key ingredients for corrosion, moisture and circulating oxygen. The sand itself, alkaline and desiccating, created a natural barrier. This was not mere luck, but often an intuitive, cultural understanding of place. The chemistry of the soil, its pH balance, its mineral content, and its ability to hold or drain water, all played a colossal, invisible role in an artifact's fate. Acidic, oxygen-poor environments like peat bogs present a fascinating case. The famous man was found with his leather cap and belt still intact, and while his iron knife had corroded, its form was preserved in stunning detail by the bog's unique chemistry. The acidic, tannin-rich waters and lack of oxygen create conditions that severely slow down metallic corrosion while preserving organic materials, effectively placing objects in a state of suspended animation. Different soils tell different stories. Alkaline soils, like those in arid regions, can be gentle on metals like copper and bronze, often allowing stable patinas to form. Heavy clay soils, which limit oxygen flow, can sometimes protect iron by creating a localized, stagnant environment. Sandy, well-drained soils might prevent the constant wetness that accelerates rust. What emerges is a pattern. Ancient cultures, through ritual, tradition, or simple practical observation, sometimes selected burial sites or storage methods that inadvertently created ideal preservation chambers. A tomb cut into a specific type of rock, a votive offering placed in a deep, still pool, a treasure hidden in a dry cave. These were all decisions that controlled the macro environment. This understanding of the world outside the artifact sets the stage for an even more intimate and intricate phenomenon. For within these chosen resting places, the objects themselves could begin to alter their own immediate surroundings, crafting a personalized microclimate for survival. Buried together, different metals can form a silent alliance. Within the confines of an ancient grave or a sunken ship's hold, a corroding bronze buckle does not just decay in isolation. It can actively shield an adjacent iron nail, sacrificing itself to create a protective chemical bubble around its neighbor. This is the microclimate effect, where artifacts become chemical islands, shaping their own immediate environments for survival. The principle at work is galvanic coupling, a natural electrochemical process. When two dissimilar metals are in contact in the presence of an electrolyte like seawater or damp soil, one metal becomes the anode and corrodes more readily, while the other becomes the cathode and is protected. It is a sacrificial relationship, one material giving itself up to save the other. The bronze, being more noble, forces the less noble iron to become the cathode, dramatically slowing its rust. But the chemistry goes even deeper than this simple partnership. The very materials surrounding the object can engineer a preservative environment. Consider the Viking swords discovered in Scandinavia, their intricate pattern-welded cores still faintly visible after centuries. This delicate Damascus-like patterning, created by twisting rods of iron and steel, is often lost to corrosion. Yet in certain graves, the specific mineral content of the soil, perhaps rich in phosphates from nearby bone or shell, interacted with the iron to form a stable, protective mineral layer called vivianite. This blue-green crust sealed the metal's surface, preserving the artistry of the smith's labor. It was not just about what was buried, but where it was buried. The presence of salts could accelerate decay, but in some cases, they could also lead to the formation of hard, stable corrosion crusts that acted like a cast, holding the original shape of the object long after the metal within had wasted away. Organic materials like leather sheaths or woolen wrappings could decay and release compounds that subtly altered the local acidity, sometimes tipping the balance toward preservation. Each artifact, nestled among its companions in the earth, was participating in a slow, intricate chemical dance. This interplay of material, partner, and environment created pockets of unexpected stability, serendipitous time capsules crafted by chemistry itself. It hints that the most enduring legacies are sometimes the result of a complex, unplanned harmony. This brings us to the ultimate test cases, the legendary objects where intentional human craftsmanship and these chance environmental blessings converge to create something that seems to laugh at the very concept of time. The shimmering, watery pattern on a Damascus steel blade is more than decoration. It is the visible signature of a metal that every expectation, a sword so refined it was said to slice a silk scarf floating on air. This legendary strength was matched by a remarkable resistance to the surface pitting and corrosion that ruined lesser blades. The secret was not in a single ingredient, but in a breathtakingly complex architecture built at a scale invisible to the ancient smiths who created it. The journey began with a specific type of raw material, the Wootz steel ingot from India. These ingots, with their characteristic banded appearance, contained just the right amount of carbon. But the true magic happened in the forge. Through a meticulous, closely guarded process of repeated heating, folding, hammering, and a very specific cooling cycle, the smith was unknowingly performing nanoscale engineering. He was coaxing the steel to form a microstructure of ultra-hard cementite nanowires embedded within a softer matrix, with recent studies even suggesting the presence of carbon nanotubes. This intricate internal tapestry is what produced the famous surface pattern, and more importantly, it created a material of extraordinary toughness and resilience. The hard phases resisted wear and deformation, while the softer matrix absorbed impact, preventing the blade from shattering. Crucially, this very same complex microstructure also hindered the spread of corrosion. Any attack on the surface met a labyrinth of different materials, stopping pits from deepening and spreading easily. The loss of the exact technique, a victim of fragmented knowledge and changing trade routes, remains one of history's great metallurgical mysteries. What we are left with is a profound realization that these artisans were manipulating matter at a molecular level centuries before we had the language to describe it. This concept of structural genius finds a powerful echo in another ancient wonder, one that took a completely different path to immortality. The Delhi iron pillar stands as a silent, 7-meter-tall testament to ancient mastery. For over 1,600 years, through relentless cycles of monsoon rain and tropical humidity, this colossal wrought iron column has resisted the fate of every other exposed iron object on Earth. Its surface is not covered in the destructive, flaky rust we expect, but in a smooth, dark gray protective layer, a kind of metallic skin that has successfully negotiated a truce with the elements. This is not a story of a lost alloy or a complex pattern weld, but of something perhaps more profound: purity and process. Modern analysis reveals the pillar's secret lies in its remarkable chemical composition. The iron used was exceptionally pure by ancient standards, with very low levels of sulfur and manganese, elements that typically create weak points where corrosion can begin. More importantly, it contains an unusually high amount of phosphorus, a result of the specific iron ore and the unique forging techniques employed by the Gupta period metalworkers. This high phosphorus content was once thought to be an impurity, but we now understand it as the cornerstone of the pillar's immortality. During forging, the phosphorus promoted the formation of a unique, stable compound called, within the metal's microstructure, is a crystalline layer of iron, oxygen, and hydrogen that forms a continuous, adherent barrier on the surface. Unlike rust, which is porous and flaky, is dense and protective. It acts as a permanent passive film, a self-healing skin that prevents oxygen and moisture from penetrating to the pure iron beneath. The pillar's sheer mass plays a crucial supporting role in this process. Its enormous volume provides a tremendous thermal mass, meaning it heats and cools very slowly with the changing day. This stability minimizes the stress caused by expansion and contraction, which could otherwise crack and compromise a thinner protective layer. Furthermore, the large surface area allows for the even, consistent formation of the film. It is a perfect storm of intentional craft and fortunate circumstance, a monument that essentially learned to protect itself from within. The result is a form of organic preservation, a living layer that has maintained its vigil for centuries. This stands in stark contrast to the next frontier of ancient anti-corrosion technology, which moved from fostering internal purity to applying an external, radiant shield of precious metal. Gold was not just a symbol of wealth, but a shield against time itself. To achieve that perfect, enduring gleam on a bronze statue or ceremonial object, ancient artisans developed one of the most dangerous and brilliant techniques in history: Mercury gilding, also known as fire gilding. Visualize the face of a Roman emperor's statue, meant to inspire awe for generations, its features permanently radiant under a skin of gold. This was no simple plating. The process began by dissolving gold flakes into liquid mercury, creating a silvery, paste-like amalgam. This amalgam was then carefully brushed or rubbed onto the meticulously cleaned surface of a bronze or copper object. The real alchemy happened next. The object was gently heated. As the temperature rose, the mercury, with its relatively low boiling point, would vaporize away, leaving behind a microscopically thin, perfectly bonded layer of pure gold. The gold itself, being a noble metal, is virtually unreactive. It does not tarnish or corrode, forming an impeccable, permanent barrier that protected the base metal beneath from the elements. But the process did more than just apply a pretty coating. The intense heat of the vaporization stage actually altered the microstructure of the underlying bronze at the interface. It could cause a slight diffusion of metals at the boundary, creating a stronger mechanical bond between the gold layer and the substrate, ensuring it would not flake or peel off easily. This was high-risk, high-precision chemistry. The dangers were immense and well-known. The heating process released toxic mercury vapor, a deadly hazard for the gilder. Historical accounts describe craftsmen working in open, ventilated spaces, often with damp cloths over their faces, a tragically inadequate defense against the invisible poison. They paid a terrible price for this knowledge, a sobering reminder of the human cost behind some of history's most dazzling artifacts. Yet, the technological sophistication was undeniable. It required a deep understanding of material properties, precise temperature control, and immense skill to achieve an even, flawless gilding. The legacy of this perilous art can be seen in masterpieces like the gilded bronze horses that once adorned the Hippodrome of Constantinople, now housed in Mark's Basilica in Venice. Though their gold surfaces have worn away in places over the centuries, the technique helped preserve the exquisite bronze sculpting beneath for nearly two. The gold acted as a sacrificial guardian, taking the brunt of environmental exposure so the art could survive. This represents a pinnacle of the high art approach to preservation, applying a precious, impervious skin. It is a philosophy of protection from the outside in, fundamentally different from the next great secret of Roman engineering, which found durability not in a precious coating, but in the chaotic, self-healing heart of a seemingly mundane material. The Romans built harbors that grew stronger with every passing wave. While our journey has focused on metal, their greatest lesson in durability may lie in a seemingly humble material, concrete. Facing the relentless corrosive power of the sea, Roman engineers did not just build barriers, they created a living stone. Their secret formula mixed slaked lime with a special volcanic ash called pozzolana, and then they did something counterintuitive. They used seawater as the mixing agent. This was not a mistake, but of chemical engineering. The combination triggered a hot, complex reaction that produced incredibly stable and rare minerals within the concrete, most notably a crystal called aluminous. Think of these crystals as a permanent, self-repairing infrastructure within the material. While modern concrete often weakens as seawater penetrates and expands tiny cracks, Roman concrete does the opposite. The crystals actually grow and interlock more tightly over decades, filling microfissures and blocking the path of corrosive salts. It is a material that actively resists its own decay, strengthening with age. This principle is profoundly analogous to the stable passive film on a well-made bronze or the layer on the Delhi pillar. In both cases, the ancients were not just creating a static object, they were engineering a system that dynamically interacted with its environment to foster its own preservation. The concrete did not merely endure the sea, it incorporated the sea into its enduring structure. This reveals a breathtakingly holistic view of material science. For the Romans, durability was not a single property added at the end. It was the foundational goal woven into the very chemistry of creation, from the atomic bonds in a crystal to the grand sweep of a breakwater. This sophisticated understanding of creating resilient, self-maintaining systems did not stop at the shoreline. It was the same intellectual tradition that would be tested in the most demanding environment of all, the open ocean, where wood and metal had to survive together under constant siege by wind, salt, and time. The open ocean was the final, unforgiving laboratory for ancient materials. Where sunlight fades into darkness, a bronze ship's fitting lies encrusted, not with rust, but with a crust of marine life and minerals. Here in the cold, oxygen-poor brine saturated with salt, the rules of corrosion change, is a relentless enemy, far more aggressive than rain or soil. Its chloride ions are tiny, penetrating agents that attack metal surfaces, breaking down protective films and accelerating decay through a process called pitting corrosion. For an artifact to survive centuries in this environment is a testament to both brilliant initial design and a kind of chemical luck. The survival of objects like the intricate bronze gears of the mechanism, recovered from a Roman shipwreck, or the heavy lead anchors from Phoenician traders seems almost miraculous. Their endurance was no accident. It began with a deliberate choice of material. Ancient shipwrights and merchants understood through hard-won experience that some metals handled the sea better than others. They favored copper alloys like bronze for fittings, nails, and sheathing. Why? Because while bronze does corrode in seawater, it often does so in a controlled, stable manner. The chloride ions in the react with the copper to form minerals like a copper chloride. In the right conditions, this can react further with seawater to create a hard, stable crust of minerals like. This crust, while altering the surface, can act as a protective barrier, sealing the metal underneath from further rapid attack. It is a compromise, a transformation that sacrifices the original surface to save the object's core integrity. Lead, used for anchors and sheathing, presented a different advantage. It is a soft, heavy, and remarkably corrosion-resistant metal in seawater. Lead forms a dense, adherent layer of lead carbonate or lead sulfate when exposed, which effectively passivates its surface. A lead anchor stock might become heavy with marine concretions, but the metal within often remains sound, its mass and chemistry granting it a slow, dignified aging process in the depths. This maritime evidence is perhaps the ultimate proof of concept for ancient anti-corrosion wisdom. These objects were not stored in carefully controlled tombs. They were thrown into the most chemically hostile environment available and expected to function. Their survival, even in a transformed state, speaks to a deep practical knowledge that was too valuable to keep in one place. This hard-earned understanding of metals and the sea did not stay secret in one port city. It traveled, carried along the very trade routes these ships were built to sail. The secrets of the forge were never meant to stay in one place. They traveled, carried not on parchment, but in the practiced hands and keen eyes of the artisans themselves. Picture a master smith from Damascus, his techniques a closely guarded family treasure, journeying with a merchant caravan along the Silk Road. He does not carry a textbook, but his knowledge is a living library, stored in the memory of muscle movements, the recognition of a metal's color at a specific heat, and the precise sound of a hammer striking a folded billet. This was the true currency of technological advancement, the silent trade of tacit knowledge that flowed alongside silk and spices. When such an artisan settled in a new land, perhaps in a royal workshop in Persia or a trading outpost in the Caucasus, he would adapt. He would survey the local ores, test their properties, and modify his recipes to work with what was available. The phosphorus-rich iron that made the Delhi pillar possible was a product of local Indian ores and techniques, but the underlying principles of careful forging and slag removal were concepts understood across the ancient world, shared and refined through contact. We can trace this diffusion like a chemist reading an ancient map. Across Europe and Asia, archaeologists find bronze artifacts with strikingly similar compositions, specific ratios of tin to copper that produce not just adequate tools, but superior, corrosion-resistant ones. These consistent recipes are the chemical fingerprints of shared knowledge. A bronze alloy perfected in the workshops of Anatolia, known for its stable patina and golden hue, appears centuries later in the grave goods of a Celtic chieftain in Britain. This was not independent invention. It was the slow, powerful seep of technology across continents, passed from master to apprentice, from one culture to the next through trade, alliance, and sometimes conquest. The migration of skilled individuals, whether voluntary or compelled, acted as the primary vector for this transfer. When the Roman Empire expanded, it did not just take territory, it absorbed and redistributed technological expertise. A metalworker from Syria might find himself in Gaul, teaching local smiths how to produce the consistent, high-quality brass needed for military fittings. Each adaptation added a new chapter to the story. In Scandinavia, local smiths, inspired by imported Roman and Eastern goods, fused outside techniques with their own traditions, creating the distinctive pattern-welded swords that would become legendary. This interconnected web of innovation means the corrosion resistance of a Viking sword might owe a subtle debt to a technique first hammered out 1,000 miles away and 1,000 years prior. It was a collective, global project in material science, conducted without a single central laboratory. This legacy of shared human ingenuity presents us with our final, modern challenge. We have these magnificent artifacts before us, but their deepest secrets are locked at a scale the original smiths could never see. To truly understand their genius, we must now peer into the heart of the metal itself, using tools that feel like pure magic compared to the hammer and anvil. Inside a silent, cavernous hall, a beam of light 100 billion times brighter than the sun strikes a fragment of metal no larger than a grain of sand. This is not a scene from science fiction, but the daily reality of a synchrotron facility, a particle accelerator built not to smash atoms, but to illuminate them. Here, in these pristine, vibration-free laboratories, the final secrets of ancient artifacts are gently teased apart, not with a chisel, but with subatomic particles. We have moved from the smoky, intuitive world of the forge to the silent, precise realm of forensic materials science. To understand what the ancient smiths achieved, we must now see what they could not, the dance of atoms and the architecture of crystals. This requires a new kind of vision, provided by a suite of astonishing tools. Scanning electron microscopy, or SEM, acts as a super-powered eye. It scans the surface of an artifact with a focused beam of electrons, revealing details down to a few nanometers, a scale where individual grains of metal become vast landscapes. We can see the microscopic pits where corrosion began and was halted, the smooth, continuous layer of a protective patina, and even the ghostly outlines of the original forging folds within a Damascus steel blade. But to go deeper, to identify what those crystals actually are, scientists use X-ray diffraction, or XRD. When that intense synchrotron X-ray beam hits the sample, the atoms within the crystal lattice scatter the X-rays in specific, interference patterns, like a unique fingerprint. By reading this diffraction pattern, researchers can identify the exact minerals present, whether it is the stable on the Delhi pillar or the complex carbides in a Viking sword's edge. Another crucial technique, atomic absorption spectroscopy, involves dissolving a tiny, almost invisible sample into a solution and then vaporizing it in a flame or graphite furnace. Each element in the sample absorbs light at very specific wavelengths, allowing scientists to measure the precise cocktail of metals and impurities with astounding accuracy. It is how we know the exact phosphorus content of the pillar's iron or the trace amounts of vanadium that might have been in the original Woot's steel ingots. These are not destructive tests, but delicate conversations with the past. The most stunning revelation from this high-tech archaeology came when researchers examined samples of genuine Damascus steel. Under the incredible magnification of transmission electron microscopy, they found something that seemed impossible: carbon nanotubes and nanowires of cementite woven into the steel's matrix. These tubular structures, engineered over a millennium ago through rhythmic heating and hammering, are among the strongest materials known today. Their presence explains the legendary strength and the unique, shimmering surface pattern, a direct link between an artisan's hammer stroke and a nanostructure we are only now learning to create in labs. This forensic approach transforms every artifact. A corroded lump of metal from a shipwreck is no longer just an object, it becomes a detailed historical document. Its elemental composition tells us where the ore was likely mined, its microstructure records the temperatures and techniques of its forging, and the layers of corrosion products chronicle its centuries-long interaction with the soil or the sea. We can read the story of its creation, its use, and its long rest, all from a silent, microscopic cross-section. This profound understanding forces a compelling question, one that moves us from pure science into the realm of philosophy. If we can now decode, with such exquisite detail, the brilliance embedded in these ancient objects, What does that recovered knowledge mean for our own future? And what does it say about the very nature of progress itself? We can map the atomic structure of a sword, yet remain unable to forge its perfect twin. This is the quiet paradox at the heart of our story, a profound gap between analysis and creation. Our advanced tools reveal what the ancients did, but not always how they thought, or why they chose one path over another. The knowledge that crafted these marvels was not stored in libraries, but in the living traditions of craft guilds, passed from master to apprentice through demonstration, story, and touch. It was an oral and tactile encyclopedia, written in muscle memory and the shared secrets of the workshop. When a master smith passed without a worthy successor, when a guild dissolved due to war or famine, or when the economic demand for a supremely crafted object vanished, entire chapters of this encyclopedia were simply erased. The precise ritual chants that accompanied the smelting of a special ore, the exact sequence of folds and quenches for a specific blade pattern, the intuitive feel for when the phosphorus content in the iron was just right, these nuances evaporated with the last practitioner. The full recipe for Wootz steel, the catalyst for Damascus blades, is a famous casualty of this fragility. We know its ingredients, we can see its nanostructure, but the living process, the rhythm and ritual of its creation, remains just out of reach. This loss forces us to confront a deeply ingrained assumption that technology progresses in a straight, ever-ascending line. The evidence of history suggests something far more organic and vulnerable. Expertise is not just information, it is a cultural artifact, woven from tradition, environment, and need. It can flourish, stagnate, transform, or disappear entirely, leaving behind only its magnificent, silent products for us to puzzle over. This realization shifts our perspective from pure admiration to a more urgent, forward-looking inquiry. If such powerful knowledge can be so fragile, what are we doing today to not only recover it, but to weave its principles into the fabric of our own future? The same principles that preserved a sword for 1,000 years are now guiding the design of jet engines and medical implants. This is the powerful, modern frontier of materials, where ancient artifacts are not merely relics to be studied, but blueprints for the future. Scientists and engineers are looking back to move forward, seeking to replicate the self-healing, damage-tolerant, and corrosion-resistant properties that ancient craftsmen achieved through intuition and skill. The goal is to create a new generation of materials that are not just stronger, but smarter, more sustainable, and inherently durable. This field, often called biomimetics, treats nature and history as the ultimate research and development lab. For example, the layered, composite structure of a Damascus blade, with its hard and soft phases woven together, is in preventing catastrophic failure. Cracks that start in one layer are stopped or redirected by the next, a principle known as crack deflection. Modern researchers are applying this same concept to create new ceramic matrix composites and layered alloys for aerospace components, where preventing a single crack from spreading can mean the difference between safety and disaster. Similarly, the self-healing passive film on the Delhi iron pillar is a dream for infrastructure engineers. Imagine a bridge or a skyscraper made from a steel that, when scratched, automatically forms a new protective layer, sealing itself against the elements. Research into phosphoric iron, inspired directly by the pillar's composition, is leading to new steel formulations that do exactly that, using controlled additions of phosphorus to promote the formation of stable, protective oxides from the very first day of service. This is not about copying the past verbatim, but about understanding its underlying logic. Ancient solutions were often elegantly minimal, using local resources and clever geometry to solve complex problems. Today, we have the tools to scale that wisdom, to design alloys at the atomic level that are pre-programmed for longevity. The potential is staggering, from biodegradable medical implants that corrode at a perfectly controlled rate within the body, to ship hulls that resist biofouling and attack for decades without toxic paints. This bridge between archaeology and advanced engineering reveals a profound truth. The past is not a closed book, but an active, open-source library of sustainable innovation. It offers tangible solutions for a world drowning in material waste, where the constant replacement of corroded and failed structures is both an economic and an environmental crisis. By learning to build things that last, as our ancestors did, we address a core challenge of our time. Yet, this entire endeavor rests on a fragile foundation. The very artifacts that hold these secrets are under a constant, silent siege, threatened by the very modern world they could help improve. A single scratch for science can erase 1,000 years of history. This is the quiet, profound tension at the heart of modern archaeology, the ethics of artifact analysis. When a researcher holds a corroded bronze helmet or a sliver of ancient steel, they are holding a finite, non-renewable resource. Every decision carries weight, balancing the urgent need to understand the object's secrets against the solemn duty to preserve its physical integrity for the generations to come. The guiding principle has shifted dramatically from the early days of exploration, where sawing a sword in half for a cross-section was commonplace. Today, the field champions non-destructive or minimally invasive techniques whenever possible. Think of it as a form of medical triage for history. Just as a doctor might use an MRI scan before considering surgery, archaeologists now use tools like portable X-ray fluorescence, or XRF, which can analyze an artifact's surface composition without ever touching it, or high-resolution three-dimensional laser scanning to create perfect digital twins. These methods allow for extensive study while leaving the original object untouched. The ethical dilemma extends far beyond the laboratory walls, however. It confronts a global shadow economy, the illicit antiquities trade. When a looted artifact is ripped from its burial site and sold on the black market, it loses more than just its legal provenance. It is violently severed from its context. The specific soil layer it rested in, the orientation it was placed, the objects found beside it, all that environmental data is obliterated. For our understanding of corrosion resistance, this loss is catastrophic. That context tells us whether the soil was alkaline or acidic, whether the artifact was in contact with other metals, whether it was in a dry, sealed space or a waterlogged one. This information is the environmental key to decoding why the object survived. Looting doesn't just steal an artifact, it burns the instruction manual that explains its longevity. Responsible stewardship, therefore, means protecting both the object and the story of its surroundings. It is about ensuring these metallic time capsules, and the knowledge they carry, remain intact and connected. This careful, respectful approach to the past is what allows us to finally ask the most direct question of all. If we could distill the lessons of these ancient marvels into a single, elemental principle, what would that core secret of preservation actually be? Phosphorus was the secret guardian in the ancient forge. In our modern steel mills, this element is often viewed with caution, an impurity to be meticulously removed because it can make steel brittle under certain conditions. Yet, when we analyze artifacts like the Delhi pillar, we find phosphorus playing a completely different role, one of a benevolent architect. Its presence, originating from the specific local ores and the charcoal used in the smelting process, was not a flaw in the recipe. It was the crucial ingredient for immortality. At the atomic level, phosphorus does something remarkable. It actively encourages the formation of a specific, ultra-stable compound called an iron. Think of not as rust, but as rust's disciplined, orderly cousin. Where common rust is loose, flaky, and destructive, forms a dense, glassy, and tightly adherent film. It bonds to the underlying metal with such tenacity that it creates a near-perfect seal. Oxygen and moisture simply cannot penetrate it to reach the pure iron beneath, effectively putting the corrosion process into a permanent state of arrest. This self-generated skin is why the pillar's surface feels smooth and dark, a testament to a chemical ceasefire negotiated over 16 centuries. Furthermore, phosphorus in these ancient irons also provided a hidden strength. It acts as a solid solution strengthener, meaning the phosphorus atoms integrate into the iron's crystal lattice and make it more resistant to deformation. So this so-called impurity delivered a dual gift, a resilient body and a protective shell. This turns our modern industrial perspective on its head. What we often scrub away as contamination was, in a different context, the key to legendary durability. It reveals that the ancient processes, born of local materials and empirical wisdom, yielded fortunate accidents of chemistry that we are only now learning to appreciate and intentionally engineer. This stands in stark contrast to another elemental player, one we more commonly associate with strength and purity: carbon. Carbon atoms are the unseen architects of strength. While phosphorus built the protective skin of the Delhi pillar, carbon was the master builder of the internal fortress, the element that gave steel its very identity. Its role is one of profound duality, a delicate balance between creating extreme hardness and managing the risk of brittleness and corrosion. Visualize the intricate, swirling patterns on a Damascus blade, those watery lines known as the damask. They are not merely surface decoration, but a map of the steel's internal soul, a direct reflection of how carbon has been arranged within the iron's crystalline lattice. In its pure form, iron is relatively soft, but introduce even a tiny fraction of a percent of carbon, and everything changes. These carbon atoms insert themselves between the iron atoms, distorting the lattice and creating immense internal stress. This stress is what makes steel, but the final properties depend entirely on the form the carbon takes. If the carbon combines with iron to form a hard, brittle compound called cementite, the steel becomes very hard but can be prone to cracking. If through a very slow cooling process, the carbon separates out as soft graphite, the result is a more malleable cast iron. The ancient smith's genius lay in controlling this transformation through fire, force, and timing. The legendary strength of a pattern-welded Viking sword or a Japanese katana comes from this intimate dance with carbon. Through repeated folding, hammering, and a precisely controlled quenching, the smith was manipulating the steel's microstructure at a level he could never see. He was creating a composite material, alternating layers of hard, high-carbon steel with tougher, lower-carbon iron. This lamination meant that a crack propagating from a surface flaw would meet a different material at the boundary and be stopped or deflected, a natural crack-stopping system. The corrosion resistance of such a blade was an indirect benefit of this complex structure. The varied composition meant that any corrosive attack did not spread evenly, but was hindered by the changing electrochemical landscape within the metal itself. This principle finds a curious parallel in a much cruder material, wrought iron. Unlike steel, wrought iron is very low in carbon, but contains long, fibrous slag inclusions, remnants of the smelting process. These slag stringers, once considered impurities, could sometimes act as a physical barrier within the metal, creating a tortuous path that slowed the inward progress of corrosive agents. It was an accidental form of protection born from an imperfect process. Yet the pursuit of the perfect edge sometimes led smiths to embrace a dangerous ally. In some early copper alloys, particularly in the centuries before tin became widely available, arsenic was added to create a harder, more silvery metal. The health toll on these ancient metalworkers, who would have inhaled toxic fumes during smelting and forging, was severe, a sobering reminder of the human cost often buried within technological advancement. Their sacrifice, however, underscores a central truth. The manipulation of carbon and its companion elements was not a science of formulas, but an art of perception, a dialogue between the craftsman, the glowing metal, and the transformative power of the flame. Arsenic's silvery glint in copper came at a terrible price. In the smelting pits of the early Bronze Age, long before tin became the standard alloy for copper, metalworkers turned to a far more dangerous partner. They discovered that by adding arsenic-rich ores to their melt, they could produce a metal that was harder, cast with sharper detail, and had a pleasing, pale sheen. This material, known as arsenical bronze, represented a major technological leap. It was superior to pure copper in almost every way that mattered for tools and weapons. But the process of creating it was a silent pact with poison. When arsenic-bearing ores are heated, they release a toxic, garlic-scented vapor. The smiths and founders working these metals would have inhaled these fumes daily, suffering from a range of debilitating health effects that were likely a grim, accepted part of their craft. Their sacrifice, born of experimentation and need, is chemically etched into the artifacts they left behind. Modern analysis of these early bronzes reveals that arsenic does more than just harden the metal. At the surface, it encourages the formation of a denser, more adherent patina. This stable layer of corrosion products, often rich in arsenic compounds, acts as a more effective barrier against further environmental attack than the patina on pure copper. So the very element that endangered the maker also helped preserve the creation, a bitter irony locked in the alloy. This story of arsenical bronze is a powerful reminder of the experimental, often perilous nature of early innovation. These ancient chemists were operating without safety protocols or a full understanding of the elements they commanded. They worked through observation, trial, and tragic error, driven by the relentless pursuit of a superior material. Their legacy is not just in the hardened metal, but in the profound lesson that advancement often walks hand in hand with risk. Yet, even the most daring experimenter was ultimately constrained by the raw material they started with. The quality of the final product, its potential for longevity, was dictated long before the furnace was lit, deep within the earth where the ore itself was formed. The final quality of the blade was forged in the stone long before the hammer ever fell. The journey toward a metal that could defy time did not begin in the smoky heat of the furnace, but in the cool, silent darkness of the earth, with the careful selection of the raw ore itself. This was the foundational, often overlooked first act of genius. Ancient metalworkers were, in a very real sense, geologists. They understood that not all rocks that glittered were equal, and the specific mountain or riverbed from which an ore was taken held the ultimate blueprint for the metal's potential. The geological fingerprint of a deposit, its unique cocktail of trace elements like phosphorus, nickel, or cobalt, was a signature that could not be erased. It was carried through every step of smelting and forging, becoming an indelible part of the finished object's chemical soul. Consider the famed bog iron ores of Scandinavia, harvested from peatlands. These ores, formed by bacterial action in acidic waters, were naturally low in harmful impurities like sulfur. When smelted, they produced an iron of remarkable purity and consistency, a material that became the backbone of the Viking Age. The superior quality of a sword or a finely wrought can be traced back in part to the cold, wet ground from which its essence was drawn. This was not a matter of chance, but of cultivated generational knowledge. An experienced smelter could look at an ore, feel its weight, observe its color and fracture, and make a judgment. He knew which seams yielded a metal that was tough and workable, and which produced a brittle, useless bloom. This empirical science, built on centuries of trial, error, and careful observation, created a direct and intimate link between landscape and artifact. The earth provided a palette of possibilities, each with its own inherent strengths and hidden flaws. But the raw material was just the beginning. It was a promising canvas, silent and full of potential. What happened next, in the fire and the rhythm of the hammer, was where human intention met geological gift, transforming stubborn stone into a legacy meant to outlast empires. The forge was a sacred laboratory, a place where fire, earth, and human will converged. Here, the smith was not merely a laborer, but a central figure in a profound alchemy, blending rigorous skill with layers of ritual and myth. His work was a form of empirical science, conducted one glowing billet at a time. He was a chemist without a formula, an engineer without a blueprint, guided by a deep, sensory understanding of his materials that was as much an art as a craft. This knowledge was not written down in manuals, but lived in the rhythm of the hammer and the color of the flame, a legacy passed from master to apprentice in the heat and smoke of the workshop. Every decision was an experiment. The smith learned through relentless trial, observing how a slight change in furnace temperature altered the metal's grain, or how quenching a blade in different liquids, water for brutal hardness, oil for a tougher resilience, or even brine or urine for specific crystalline structures, could mean the difference between a legendary sword and a shattered one. These were not random choices, but a refined, generations-deep research and development program. Each successful blade encoded complex metallurgical principles like thermal cycling, carbon diffusion, and strain hardening into a repeatable practice, centuries before those terms existed in any textbook. The true secrets, however, resided in the tacit knowledge, the intangible cues that defined mastery. It was in recognizing the precise cherry-red hue that signaled ideal forging heat, a color language lost in photographs. It was in the distinctive ring of the hammer striking metal at just the right pitch, indicating proper consolidation. It was in the feel of the metal's resistance under the tool, a tactile conversation between craftsman and material. This sensory feedback loop was the smith's most precious tool, and it is the part of the legacy that is most fragile. We can preserve the sword he made, but we cannot preserve the subtle, instinctive wisdom in his hands the day he made it. This deep, experiential understanding was so valuable, it was often wrapped in secrecy and spiritual significance. In many cultures, the smith's role carried a near-mystical weight, associated with gods of fire and creation. The rituals performed at the forge, the chants, the specific timing of actions, these were not mere superstition. They served as mnemonic devices, structuring a complex technological process and protecting its vital steps within a shell of tradition and reverence. The smith held the power to transform earth into enduring artifact, a power that demanded respect and secrecy. This guarded, ritualized transmission of skill stands in stark contrast to the fate of the objects themselves. While the knowledge was fragile and human-bound, the products of that knowledge were built to outlast their makers, silent emissaries carrying a coded message about human ingenuity into a distant future they could never see. The very rust we strive to prevent writes its own chronicle. What we perceive as decay is, in fact, a meticulous chemical diary, a layered archive recording every chapter of an artifact's long life. This corrosion biography transforms a simple object into a complex historical document, its surface etched with data about time, place, and journey. By learning to read this language of transformation, archaeologists can unlock stories that the original makers never intended to tell. The process begins with the most basic question: how old is it? While not as precise as carbon dating for organic materials, the thickness and sequence of corrosion layers can provide powerful relative dates. A bronze coin recovered from a shipwreck, for instance, will have a specific crust of marine minerals. By comparing this crust to coins of known age from the same wreck site, researchers can build a timeline of deposition, understanding which artifacts settled first and how the wreck site evolved over centuries. But the record goes far deeper than mere age. Each environment leaves a distinct chemical signature. A copper alloy object buried in the acidic, peaty soil of a bog will develop one type of green patina, rich in chlorides and sulfates. That same object, if it had spent its life in the dry, alkaline sand of a desert tomb, would wear a completely different mineral coat. By analyzing these corrosion products with tools like X-ray diffraction, scientists can effectively reconstruct the object's final resting place, determining whether it lay in a forest, a field, or the seabed. This environmental fingerprint becomes a powerful tool for tracing movement. Imagine a Roman bronze figurine found in Britain. Analysis might reveal that its innermost corrosion layer matches the mineralogy of soils in Italy, suggesting it was crafted and used there initially. Subsequent layers could then tell a story of travel, perhaps showing exposure to maritime salts, indicating a sea voyage, before finally acquiring the local crust of its British burial site. This data can confirm trade routes, map the spread of cultural objects, and even hint at looting or reuse in antiquity. The corrosion record can also capture singular, catastrophic events. A bronze statue recovered from the ruins of an ancient city might show a sharp, distinct layer of soot and ash fused into its patina, a permanent chemical scar from the Great Fire that consumed the temple it once adorned. Similarly, the pitting and mineral deposits on armor could indicate whether it saw battle near the sea or was stored peacefully in an armory. This narrative in chemical form completes a profound circle in our exploration. We began by marveling at objects that resisted corrosion, seeing their pristine surfaces as the ultimate victory over time. Now we see that even in succumbing to decay, metal has a voice. The relentless process of oxidation, which the Delhi pillar so elegantly halted, becomes, for other artifacts, the very pen that writes their history. This duality is essential. It reminds us that preservation and transformation are two sides of the same coin, both offering invaluable windows into the past. One shows us the height of human intention, the other reveals the unfolding story of what happened next. Legends whispered that the Delhi pillar was forged by gods, or that a Damascus blade contained the captured soul of a dragon. When an object performs the impossible, surviving centuries against all odds, the human mind naturally reaches for explanations that transcend the mundane. For generations, the preternatural endurance of these artifacts was wrapped in stories of divine blessing, alchemical magic, or the work of supernatural craftsmen. It is a beautiful human impulse to mythologize the extraordinary. Yet the true story, revealed by electron microscopes and diffraction patterns, is in many ways more wondrous. The magic was real, but its source was not in the heavens. It was in the earth, the fire, and the meticulous hand of the smith. The supernatural narrative, while captivating, ultimately obscures the profound human achievement at play. It takes the credit away from the generations of artisans who, through careful observation and relentless experimentation, learned to command the very building blocks of matter. Their spells were precise hammer strokes and controlled cooling cycles. Their divine intervention was an intuitive grasp of phosphorus content and carbon distribution. By gently setting aside these myths, we do not diminish the artifacts. We elevate the people who made them. We shift our awe from the imagined to the accomplished, recognizing that the capacity to engineer materials at such a sophisticated level existed long before the formal scientific method. This clarification is not about dismissing cultural beliefs, but about honoring the tangible, replicable genius they point toward. The pillar did not stand because a god willed it, but because a craftsperson understood on some fundamental level how to persuade iron to protect itself. That distinction is everything. It transforms these objects from mystical relics into direct messages, a form of communication across time written in the language of crystal structure and chemical bonds. They are not saying, magic was here. They are saying, pay attention, this is how we did it. This realization opens a door, not to a lost world of sorcery, but to a living library of sustainable technology. If their methods were not supernatural, but supremely natural, then their secrets are not lost to us. They are simply waiting to be fully understood and adapted. This leads to the most practical and urgent question of all. In a world facing immense challenges of waste, decay, and short-term thinking, what would happen if we truly listened to what these ancient masters are trying to teach us? The carbon nanotubes found in Damascus steel are not just a curiosity, they are a direct challenge. They prove that ancient craftsmen, through fire and hammer, were performing what we now call nanotechnology, manipulating matter at the molecular level to achieve properties we are still striving for today. This is not a metaphor, it is a historical fact written in iron and carbon. The frontier of modern materials science is precisely this, the deliberate design and assembly of materials atom by atom, molecule by molecule, to create substances with unprecedented strength, lightness, and resilience. We are building from the blueprint up, while they discovered the blueprint through relentless, hands-on experimentation. The convergence is breathtaking. We now have tools like molecular beam epitaxy to deposit single atomic layers, or focused ion beams to sculpt materials at the nanoscale. Yet, the goal remains the same as that of the Damascus smith, to create a material where the architecture itself confers legendary performance. This suggests a thrilling future path, one where our most advanced labs do not work in isolation from the past, but in active conversation with it. Future research, using ever more sensitive instruments, will likely uncover other nanoscale phenomena hidden within artifacts we thought we understood. What if the iridescent sheen on certain ancient glasses, or the peculiar toughness of some ceramic glazes, also stems from nanostructures engineered by accident and preserved by time? Each discovery would be another piece of a grand, distributed research and development project that has been running for. The synthesis holds immense promise. Imagine a new class of smart materials inspired by this ancient wisdom, alloys that not only resist corrosion but sense stress and repair micro cracks, much like the self-healing passive film on the Delhi pillar. Or composite materials that mimic the layered, crack-deflecting structure of a pattern-welded sword, but for the airframes of tomorrow's aircraft. This is not about copying old recipes, but about understanding the deep principles they embody, principles of heterogeneity, of self-organization, and of harmony between material and purpose. The forge of the past and the of the future are speaking the same language, one of structure and property. The next great leap in creating things that last may come not from discarding old knowledge as primitive, but from recognizing it as a different, profoundly sophisticated kind of science. It invites us to see these ancient artifacts not as endpoints, but as starting points for a new, more sustainable chapter in human ingenuity. The silent guardians of history are not just in museums, they are in the principles they embody. Our journey has revealed that the battle against corrosion was never a single, simple trick, but a holistic philosophy of creation. From the precise phosphorus content in an iron pillar to the self-healing chemistry of Roman concrete, ancient solutions speak of a profound harmony between material, maker, and environment. They achieve durability not through force alone, but through a sophisticated dance with chemistry, one that respected the natural world enough to guide its processes toward preservation. This legacy reframes our entire view of technological progress. It shows that innovation is not a straight line from primitive to advanced, but a vast landscape of potential knowledge, where brilliant solutions can emerge, be forgotten, and patiently wait to be rediscovered. The artifacts we have explored are more than objects. They are conversations across time. They ask us to look beyond the surface, to see the intentionality in an alloy's mix and the foresight in a chosen burial site. They challenge the notion that older means simpler, proving instead that human ingenuity, when driven by need and refined by observation, can achieve feats that still leave modern scientists in awe. This exploration is an invitation to see the built world around you with new eyes. The stainless steel in your kitchen, the coated blade of a tool, the protective paint on a bridge, all carry echoes of that ancient pursuit. The past is not a sealed vault of lost secrets, but a living library, its pages written in crystalline structures and stable patinas. If the idea of unlocking more of history's hidden sciences intrigues you, consider subscribing to continue this journey of discovery. We would love to hear which ancient marvel of material science you find most compelling. Share your thoughts in the comments below.